Here's a fun problem that looks like a trajectory problem, but it's really simpler than that. It's really just a constant acceleration problem. But it's kind of a tricky one, and I'd like to show here how we can approach a problem like this. I haven't curated my answer, I haven't gone through the solution to this, but I'll show how we can approach a problem like this, how we can take apart a problem like this, and then put it back together. And then maybe later, once we've got the answer, we can go back and find a more elegant way that looks logical to find the answer. So our situation is that a cannonball is dropped to the ground. So that's pretty simple. It's just acceleration at the rate of g. We're told how far it drops in its last second. How exactly that relates to the constant acceleration kinematic equations isn't immediately obvious. We might want to go through the different equations. It might also be good just to take stock of the scenario and see if there's anything that jumps out about it. It's certainly not going to hurt to draw a couple of diagrams at the beginning just to get a pictorial sense of what's going on. So I can start with just saying it's dropped from some height above the ground, which we don't know. It's got some acceleration, and I'll call it g. I'll just make the downward direction positive, so I'll just do that. I'll just specify that this is the plus y direction, because it's going to be falling down and we're finding out how far it's fallen down. So that makes sense to make it the positive direction instead of having a bunch of canceling double negative signs or anything like that. And then we know that as it falls, we'll have t minus 1 second, and then at t. And in this distance, we've got some delta y, which we're told is 70 meters. Well, what can we do with that? Well, it's a constant acceleration situation. That tells us the velocity in a particular time. It was the initial plus acceleration times time. And here, with y being the positive, that's going to be what we got. Our y is going to be, well, we'll start it at 0. Right there. And so then our y is going to be 0 plus v naught t plus 1/2 gt squared. So what does that mean? That means we get a plot something like this. If this is our y and this is our time, then the y looks something like that. And our velocity time plot, might as well sketch one of those two. And the velocity starts at 0. And we know that the slope equals g. So what else can we do with this? We say in its last second, it travels a distance of 70 meters. And that also means that the delta v is going to be a delta t, right? That's the velocity is the acceleration times the time, or at least the change in velocity. Let's assume that a is it's g, so let's say it's about 10 meters per second per second. So that means that the velocity at the end, so v at t, equals the velocity a second before, t minus 1 second, plus 10 meters per second. And we also know the average velocity equals the how far it's gone in how much time. Well, in that last second, it's going to be 70 meters divided by 1 second. Oh, so its average velocity is 70 meters per second. But it changed 10 meters per second over that time. That means that the speed at time t is going to be about 75 meters per second. And the velocity at t minus 1 is going to be 65 meters per second. Well, we've got, so this tells us v at t, that tells us the velocity when it hits the ground. Well, we've got a couple of kinematic equations that we know how to work with. We've already shown a couple of them. The velocity equals v naught plus at in the y equation. We have a couple others that we got from combining these that we said would be useful. So let's write down what those are and see if we can see if they apply to our situation. One of them took the time out of the situation and just had the acceleration the initial velocity and the final velocity. And that looked like this. It said that the velocity at some time minus the velocity at some time before is 2a, and here it's going to be y minus y naught. Well, what can we do with that? Now here earlier I talked about the difference between time at the time of landing t and 1 second before, but now we can look at the time at time of landing and when it's dropped. So we don't know how far it dropped, but that's what we're trying to find out. So this y minus y naught is what we're trying to find here. What height above the ground was it dropped? We know that it was dropped from rest, so that tells us that v naught is going to be 0, and v we know was 75 meters per second. Let's see if we can do something with that. So we have v squared equals 2g, and then, well, what's our y minus y naught? Well, our y, we're saying when it hits the ground, that's going to be 0. So that's going to be 2g times 0 minus y naught. We're trying to find y naught. In fact, that'll be our answer to our question. So all that we have to do there is divide both sides by, well, it looks like we might run into a problem with the negative. Aha! So that's what I did wrong. I did do something wrong here. This is part of the process of working through a problem. So what I did wrong was I wasn't consistent with my directions. Here I've defined the positive direction as down. Here I'm saying y minus y naught, where y is the end and y naught is the beginning. And that's fine. But if I'm trying to find out y naught, well, I know y naught is 0. It's the ground that I don't know, because I said we're starting off at 0. And so the ground distance is what I don't know. So actually what I'm trying to find is the y, the height at the ground, or the distance of the ground from the start. How do I fix what I did to make that happen? If this is saying y minus y naught, so y, yeah, that's the final distance. That's what we're trying to find. Y naught is 0. So it's going to be y minus 0 here. So I'll erase this. And instead of finding y naught, it's y that I'm trying to find. There we go. Now we're fixed. So now we're trying to solve this for y. And all we have to do for that is divide both sides by g. And with our really rough back of the envelope calculations, approximating that g is about 10 meters per second, we can say this is v squared. Well, v we said was 75 meters per second at the end, so I have to square that. So that's 5625 meters squared per second squared divided by 20 meters per second squared. And so what I'm going to get is 5625 divided by 20, and that's 281 meters. And some change. Now, that was a perfectly valid way to approach the problem, but it gave us an answer that's numerically incorrect. If we want to get a numerical answer that will be marked right, we need to use the correct value for the acceleration, which should be 9.8 meters per second instead of 10 meters per second. So this formula is still valid, but we found the v using the wrong g, and we have the wrong g in it. So we'll need to use different numbers here. So first, for the velocity at time t, instead of 75 meters per second, it's going to be 74.9 meters per second. Not a big difference, but when we square it, that might change some things. So to put in the proper values, we'll have 74.9 meters per second, and we square that. (5610.01). And then when we divide by 2g, that's going to be 19.6 meters per second squared. And this is meters squared per second squared again. And here we get a slightly different answer of 286 and some change, 286.225. To the significant figures that we have, 286 is correct. Now before, we did a lot of heavy lifting with the realization that the average velocity was related to the velocity at the beginning and the end, and so that we could calculate what the velocity was at the end. If we didn't have that flash of insight, can we still get to the problem? Sure. We probably won't get there as quickly, but we ought to be able to do it. So let's work this through, this time by brute force, to see what we can come up with. Let's write down the constant acceleration kinematic equations that we know. V equals V naught plus AT, which in this case is just going to be AT. We've got Y equals Y naught plus V naught T plus 1/2 GT squared, which in this case is just going to mean 1/2 GT squared. We've got the equation that takes the acceleration out of it, Y minus Y naught equals 1/2 V naught plus V times T. This was qualitatively saying that the distance traveled is equal to the average velocity times the time. This formula for the average velocity only applies to constant acceleration. The final kinematic equation that we have was the one that had the time taken out of it. So just related distance and the initial and final velocities. So is there any of these that we could use? We're told in the last second. So at some time and at another time there's a difference in distance. That sounds like we might be able to use this equation. We'd have to use it twice. So we'll say y at time t, or maybe instead of calling it time t, I'll call it y at landing, equals 1/2 g t at landing squared. And then y at landing minus 1 second equals 1/2 g t landing minus 1 second squared. And we know what the difference is between these two. So we have y landing minus y landing minus 1 second equals 70.0 meters. It's a known value, and I'm going to call it delta y for notational simplicity. So let's combine these two. So we have delta y, which is a known quantity, equals yl minus yl minus 1 second. I'll just call it L minus 1 for, again, simplicity. So we'll just substitute in the values here. So this is YL, 1/2 GT squared, and then we're going to subtract from that 1/2 G TL minus 1 second. And we square that. The next step is going to be to simplify. So we'll want to expand what's in here, then combine any like terms that result. So this will be t sub L squared minus 2 t sub L times 1 second plus 1 second squared. Distribute that 1/2 g through it. Actually, what we can probably do is just factor out the 1/2 g from both sides. So 2 delta y over g equals TL squared minus TL squared. So that's going to cancel, plus 2 TL seconds minus 1 second squared. As I said, these are going to cancel out because they're negating each other. So again, what we're trying to find is TL. Actually, is that what we're trying to find? That's not exactly what we want to find. What we want to find is from what height. So we're trying to find y, essentially, at landing. But if we find t at landing, then we can just substitute that into this equation and get the y at landing. So we're good. Finding t at landing is not a bad thing. I was just kind of mindlessly applying the equation, but then once we got far enough that we saw that we could do something with it, now we could try to figure out if what we can do with it is useful. And yes, we can pull out from this what we want. So let's continue. The only expression with t sub L is this term, so we'll take the 1 second out of here. 2 t sub L times 1 second. I'll put the 1 second in there explicitly so that we don't think that the s is some kind of a variable. 2 delta y over g plus 1 second squared. And then we're going to divide both sides by 2 seconds. 2 delta y over g plus 1 second squared. That whole thing we're going to divide by 2 seconds. Now we can just plug numbers in. 2 delta y, so delta y here is 70 meters. So 140 meters divided by 9.8 meters per second. What does that give us? That gives us something that's going to be in terms of seconds squared, so that's right. Plus 1 second squared. And then we divide that by 2 seconds. Are our units going to work? It looks like they will. Now it's just a matter of doing the numbers. 140 divided by 9.8. That's 14.28. We're going to add 1 to that, so that's 15.28. And that's going to be seconds squared divided by 2 seconds. And that'll give us a number that's just in seconds. So 7.14 seconds. Then what do we do with that? Well, we said we'd find our y sub l, which is going to be our answer. So we're going to plug it into this formula here. So y sub l is 1/2 g and then TL squared. So that's this mess. Perhaps it would be more careful to, perhaps it would be more rigorous to substitute this in, and it looks like the 1/2 g would cancel out in this term, but not in the other terms. So we might not gain any additional insight. Let's just run the numbers. So 7.14 seconds, try to write that legibly. So multiply that by 4.9 meters per second. And I get 35. Meters, which is not at all what we got before. What we got before was much, much bigger. So what went wrong here? Well, I'll tell us what went wrong here. I didn't square it. That will do it. So let me be a little more explicit here. So 7.14 seconds, we're going to square that. And let's get all our numbers in here. So that's 4.9 meters per second times 7.14 seconds squared. So the seconds squared are going to go away and I'll end up with just meters. That's good. So 4.9 times 7.14 times 7.14 gives us about 250 meters. The old one said 287 meters. So let's go back and figure out what's going on here. Oh, well, that looks like a difference. It looks like I made a mistake in the calculatoring. So let me try that again. 140 meters divided by 9.8 meters per second plus 1, 15.28. So far this part seems to be right. And when I divide that by 2, instead of 7.14, guess what I did? Oh, I must have forgotten to add 1. Because if I do 14.28 divided by 2, that gives me 7.14. But if I do 15.28, it gives me 7.64. So let's go back and fix that. So that gives me 7.64 seconds. And then I'm going to use 7.64 in here. So now let's try these numbers. 4.9 times the square of 7.64. And this time I get 286. And that is, in fact, what we got from the time before. So that is showing us that we get the same answer both ways, if we don't screw up.